Welcome back, everybody. We are so happy to have Maria to help to teach us about more about the combinatorial skewing formula. So I'm not going to take too much of your time, Maria. You can go ahead.
Okay, thanks, Anna. So yeah, I didn't even put a title today really, but I'm starting this lecture out with a combinatorial teaser because I know a lot of this gets very technical. So we're going to enter the combinatorial proof of what I was talking about last time, but this is just sort of a little sort of lemma that was actually the key lemma we needed to prove. And it just turns out to be a kind of fun combinatorial puzzle. So I'll just give you the puzzle, and this way you can, if you want to think about it on your own, you'll be able to think about it before the next lecture whenever I actually get to how it works. So the teaser is we define a tuple alpha to be an allowable content. So say alpha is an m length tuple and the numbers can be anything from 0 to m. And it's an allowable content if the first entry is bigger than 0, so you can't have 0 as the first entry. And then whenever you have a positive entry, so for any j for which alpha j is bigger than 0, then the next alpha j minus 1 entries are 0. And I should make this clear with parentheses. I mean, you take alpha j and you subtract 1, right? The minus 1 is not in the subscript. And the entry after that is then positive. So there's exactly, if you have a positive entry t, there's exactly t minus 1 zeros after it in a run of zeros. So let's just do examples and see whether or not these tuples are allowable. So for instance, this starts with a positive entry. That's good. And after a 2, there has to be a run of exactly 1 0, 1 less than 2, right? And then another positive entry. And after a 1, there's no zeros because you subtract 1 from 1. So you can just go to the next positive entry after that. And after a 2, there has to be a run of exactly 1 0, and we're done. So yes, this is allowable. So my question to the audience is this one allowable? So Monica gives thumbs up because let's see, 3 is followed by a run of 2 zeros. That's good. But is the 4 followed by a run of 3 zeros? No. So you have to have 3 zeros following the 4. You're not allowed to sort of cut off the run of zeros at the end. So actually, no, there's not enough zeros after the 4. But this one's okay because we had the entire run of 1 0 after the 2. And similarly, let's look at this one. So the 2 is followed by a run of 1 0, and then the 3 is followed by a run of 2 zeros, and that's exactly right. So then the sort of next entry after the run of zeros can either be the end of the word or another positive entry. And so what you'll see is that when we have these restrictions, this one's allowable because ones don't have to be, so this one's yes. Ones don't have to have anything after them. Ones are sort of free. And you'll see that the ones that are marked yes, the sum of all the entries is 5. In this case, the length of the word is 5, and also the sum of the entries is 5. Because of this rule of how many zeros you pad with, it actually keeps the sum constant as well. So that's an easy sanity check as well. This one is fine because 3 is followed by 2 zeros, and then each of the ones are not followed by any zeros. So yes. This one is not okay. Can anybody tell me why? And you can use the chat or raise hand. Okay, Monica, go ahead.
Yeah, I have to redeem myself because it ends in a 3, but then does not have zeros after the
Right,
3.
the 3 doesn't have any zeros at the end. Okay, so now we're
If
now
it
we're getting
exists,
it.
caught me at the original description. Now I understand.
Yes. Yes, exactly. Well, this is why I do so many examples that everybody knows what the tuples are. And then this one is very fun. This was 5 followed by a run of 4 zeros, and that is yes. So you might also get the sense that there's a finite number of these, right, for any given length, for like length 5. So one exercise that's fun to do, that's for all combinatorialists to enjoy, is how many allowable contents of length m are there. There's a nice explicit formula. And then what we're doing with these allowable contents is looking at words that have that content, right? So for instance, the word 13414, just like we were doing last time with the monomials, this has content to, sorry, I'm writing with an eraser, there's 2 ones, so we write down a 2 for the first entry, and then there's no 2's, so we have a 0. That's good because a 2 has to be followed by a 0. And then the 3 is 1, and then there's 2 4's, and there's no 5's because we go up to length 5, right? Because it's a 5-letter word. And this one is allowable. So W is an example of a word with an allowable content. So Dale says each content is characterized by where the non-zero entries are. Good. Okay, so for the exercise, that gives a huge hint on how to solve that exactly. And then for now we define an inversion on words. We're going to start introducing these INV statistics in DINV. An inversion in a word is a pair of entries, I to the left of j, with I greater than or equal to j. So I call this a possibly tied inversion. We're allowing ties in our inversions when we count them. So let's say like 4 and 1 and 3 and 1 form inversions, but so do 1 and 1 and 4 and 4 here. So there's 4 inversions in this word that we have. And the actual exercise, this is sort of the key lemma for one of the many key lemmas for the combinatorial proof. What it boils down to is showing that this alternating sum equals 1. And it's actually a Q analog that sums to identically 1 as a Q analog. So what we show is that if we sum over all words with allowable content of length m, of -1 to the number of zeros in the content, times q to the inf of the word, then all the q's cancel and you just get 1. And so as an example, here I've worked it out for m equals 3 to show you that this works. So the allowable contents are 111, 201, 120, and 300. This has no zeros, this has 10, this has 10, and this has no zeros. So the signs will be plus, minus, minus, plus on those words. And here's the words of allowable content 111. So these are positive, with q to the inv written to the right of them. And then here's the ones with content 201. There's 2 1s and a 3, and they're Q analogs that you add together. These are the ones with content 120, and here's the only one with content 300. And if you just add up all these Q powers, you'll see that it's 1. So the question is, why is this true? And this is why I said there's going to be a sign reversing involution that we use to cancel some of these pairs. So it's a fun exercise, and you can think about it. And we'll get back to where this comes up in the actual combinatorial proof, but somehow this is all what it boils down to. So let's go back to the overview of where we were. And we did the algebraic proof last time, or we outlined it at least. And so today and the next time, and possibly the next time after that, if I need more time, is going to be focusing on the combinatorial proof of this skewing formula, starting from
Maria,
these. Sorry, was
sorry.
there a
Can
question?
I
Yeah,
ask
go ahead,
you,
Martha.
can I ask you a quick question before you go on?
Yeah.
Did you say that you had some formula for the enumeration of the number of words? Like if you took all the words that are allowable for a given alpha of a specific length?
Oh, instead of how many contents, you're asking how many words.
Yeah. So
Uh,
you have allowable contents, and then you also wanted to count how many words. I was just wondering if it was the law numbers based on your example.
I don't know, but that's a good question. And I don't think we enumerated that. Actually, that's a really good
Okay.
question. I think, I mean, the way I would count it is I would be like, well, for each allowable content, it's all the permutations of that. So you'd have some multinomial coefficient, I guess. Like I would just add up, I mean, in this case, I would be adding up like 3 choose 111 plus 3 choose 21, right? 201 plus 3 choose 21 plus 3 choose 0, right? So I'm like taking all the allowable contents and adding the proper multinomial coefficient. I don't know what that is.
Okay, thanks.
Probably it's something nice. Well, for m equals 2, I know it's 3. Sorry, that.
Ah, okay.
For
And
m equals 1, there should be only 1, right? Because it's just like the word 1. So 1, 2, and then this is what 6 plus 6 plus 1, 1, 3, 13 is the first. Okay, if anybody wants to
yeah,
enter that into OEIS, you can. Let me know what it is.
I mean, that is the first three law numbers. I was thinking about law numbers in a different context. So I was just curious that you got 13 because I was thinking about exactly that yesterday. And
Oh,
nice.
okay. Well, it probably is. I mean, maybe somebody can take the time during this talk to calculate the
Thank you.
double check. So
Thanks
let me
for,
know, Martha. Yeah, thank you
okay.
for telling me that. Um, that's cool. Yeah, I haven't actually asked myself that question. Um, so yeah, so we're gonna focus on the combinatorial proof here. And so what we need to do is define these two formulas for the rational shuffle and delta polynomials that I hinted at in the first lecture. And so this will be the actual first definition I give of these two sides of the equation. So now you'll be able to actually calculate with them. So the combinatorics definitions, which is really coming from the Rise delta theorem for the delta polynomials, is we're using this notion of a stacked parking function, defined by Hagelin, Remmel, and Wilson. And this involves, instead of just taking the diagonal of a rectangle, you actually have a stack. And let me just sort of point here. These green squares are stacked up. It's like you have one square in each row. Each column contains at least one square, and as soon as you finish, putting down your squares in one column, the squares in the next column start on the row one level up. So it kind of forms a path going up and right in your diagram. And then you're looking at all dict paths that lie above your stack. So the paths don't even have to lie above the diagonal. They actually just lie above the stack that you chose. And then you can make a parting function on this, like if you label the rises again. So I'm gonna.
Maria,
Oh yeah.
question. For the stack, that very first column, do you get your choice of how tall you make it?
Yes. So this is just one example of a stack, and we're gonna be like fixing a stack or summing over stacks depending on what we're doing. Let me just say, let's see. So I could have made it like your first column stack be like height 3 if you wanted instead, and then your second column stack could have been height 3 as well. That would have put us up to like here already, I guess. And yeah, then I could have done like 2 and 1 or something. So that's another example of a stack.
Okay, and they never have to reach all the way up to the top red line, even at the end?
Yeah, and I should say what I'm doing is I'm taking an n by k rectangle. I don't know why there we go. And so in an n by k rectangle for the delta polynomials, delta prime ek minus 1 ek, we're taking an n by k rectangle and first filling it up with a stack like this. And then we're considering dict paths that lie above that stack. So it's like a dict path with a stack under it is another way of thinking.
Okay,
Yeah.
great, thanks.
And so then I'm still just labeling in terms of where the labels go. They don't go in the stack. They go still to the right of the up steps of the parking function. So we have that kind of notion. And we define the area and HDIM statistics on this as follows. So the area is the number of boxes that are above the stack and below the path. And I'm going to write D for dict path a lot. Sometimes, usually P is parking function. So if D is going to be my path. And that means that, we have, maybe if I use a different color to highlight, these 4 yellow squares that I'm filling in right here are the ones that are above the stack and below the path. And so the area is going to be 4. And the HDINV is formed by first expanding this funny stacked thing into an ordinary parking function by sort of taking each stacked column, like say this height 2 green thing, and just sort of laying it sideways. So I would turn a green stack. Let me draw how this works. So if I had a stack of height 3, say, then I would just sort of move over each square starting from the bottom. And what you do to the dict path is you add a horizontal step. So I'm going to highlight over here. This extra step is formed by just moving over one step before I sort of connect to the rest of the dict path. So for instance, this height 4 column laid out into this length 4 diagonal, and I have 3 extra right steps. And then we just copy over, like the up steps are still the same, so you just copy over the labels like this. Okay. So Fubini numbers. Okay. So in the chat, we've figured out what these numbers might be. And I don't know what the Fubini numbers count besides maybe this, number of allowable content words, but that's exciting. So, yeah, so and anyway, the way we define HDINV is just the div of this expansion that we do over here to make it a square parking function, n by n. And then the div is the number of inversion pairs that are either on the same diagonal, A and B, with A less than B. So for instance, 2 and 7 would form an inversion pair because they're on the same diagonal and 2 is less than 7. Or you could have them one off diagonal, and the smaller number is up and to the right of the larger number. So 7 and 5 do not form an inversion in that way. But 5 and 9 are on the same diagonal, so they also form an inversion. As far as inversions on the next diagonal up, we have 1 and 3. And then we have some off diagonal inversions, like 3 is one off diagonal from the 8, and so is the 1 is off from the 8, and so those two form an inversion. And I believe That's it. So dinv is going to be 1, 2, 3, 4. So we have 5. So hdinv is going to be 5 in this case. So you don't actually compute the hdinv right on the stacked parking function. You just expand it and compute ordinary parking function dinv.
Can you remind me how you get the labels going up? The like 2, 5, 6, 8, or is this just one?
Right. So the labels are actually, I'm just writing down any parking function. So
Okay.
they're just
All
any
right.
column labels that increase up the columns. And I'm
Okay.
being a little bit sloppy here because I am generally allowing repeats, but you can't allow repeats in the same column. So
Thank you.
this is what I defined last time. That's right. And
Okay,
so
thank
yeah, we write like we're gonna write like WLD stack NK for the set of these, and what W means is repeats are allowed, so it's a word labeled dict path. LD is for labeled dict path, and then stack means, oh, we have a stack and it's N by K. So that's that's going to be the notation we use for this this set. So yeah, and good thing I just defined that, because the rise delta formula says that this gadget that we're trying to understand and link to rational shuffle is the sum over all parking functions that are these stacked parking functions of q to the area, t to the hdinv, x to the pi. So now we finally understand what this delta polynomial is that we're working with. Okay, so now we have, it's confusing because we have so many different types of parking functions in this talk, because rational shuffle is also defined for a rectangular shaped parking function with different statistics. So I'm going to try to, be as clear as I can about these. But now remember, we had this parameter k for rational shuffle, this big K, where as opposed to little k, big K is a multiple of little k. Big K over little k here is n minus k plus 1, which in the diagram I drew above is 2. So I think of big K over little k as the slope of my diagonal line, right? So that has slope 2 in this case because I have 8 by 4 in the example. And that means you can solve for n, and so in this case n equals 5 and k equals 4. What you can do with this is make a parking function now. Let me get my example out. So say I filled these boxes. So now we don't have any stack or anything. We just take a normal parking function. Again, I'm being lazy by not dealing with ties. I really should be, but we're going to fill it with the numbers, say 1 through 8. The columns are increasing. And basically with ties, I should say that I'm not counting ties as divs when I do have ties. That's the only thing you need to know. And it's a little funny because I know in the teaser I said I'm counting ties as inversions, but here I'm not. And it's because there's actually like a complement flip we do in the middle of the proof that we'll need to apply at some point. But at this stage, we are not allowing ties to be inversions. So the area, again, is the same thing, the number of boxes whose interior is fully above the diagonal. So fully above the diagonal, because we don't have a stack this time. So let me again now color in yellow. Oops, let me highlight. The 7 and the 4 are both fully above the diagonal. So the area is 2 in this case. And the dim statistic for the rational shuffle theorem is extremely complicated. It's actually a sum of 2 dim statistics minus another dim statistic. So it's going to be path dinv plus t dinv minus max t dinv. So I'll break each of these down. T dinv is the easiest because it's the number of diagonal inversions, but just taking the slope to be different. So the same thing as before, where you can either have an A above B on the same diagonal. No, the other way around. A below B on the same diagonal, or 2 sort of adjacent diagonals, but this time they're slope 2, right? So you look at sort of over 1 and up 2 each time, and you'll have the A here and the B here. So if we were going to look for inversions in this example, like the 2 and the 1 are on the same diagonal, but they're not in the right order for that to be the case. And but the 2 and the 8, no, that's not right at all. The 8 is not on the same diagonal as the 2. Hang on, what am I saying? The 5, yeah, sorry. 5 and the 8 are on the same diagonal because they're both sort of 1 above, sitting on the slope 2 diagonal. And 5 is below 8, so that forms an inversion. Also, the 1 and the 5 are sort of off diagonal from each other, so they form an inversion. And the 3 and the 7 similarly form an off diagonal inversion. And then you can see the 3 and the 8 are on the same diagonal, and that does go up, so that's valid as well. Finally, okay, I'm just going to write down what they are. You can check this. The 6 and the 5 also are a diagonal inversion. They're a little harder to see in this case, but if you count them all up, you'll see t div is 6 in this example. The max tdiv now is not so bad to understand. It's the max div of any parking function that has that dict path, which basically means the total number of attacking pairs of squares that could be inversions. So in this case, our max tdiv is, I'm just going to sort of give it to you in this example, is 12. And the path div is a completely different statistic that only depends on the path. It's the number of squares above the path, so that if S is the slope, right, k over k, then the leg of your square is related to the arm in the following way. So leg means, let me draw a square and draw what leg and arm means. This square that I starred in the upper left has leg 4 because there's 4 squares below it, and its arm is 1 because there's 1 square to its side before you hit the dig path. So maybe I should draw this. If we have a square here, this is the leg and this is the arm. Okay. So you have an arm and a leg going over and down. And the leg has to be roughly S times the arm. So like it has to sort of match the slope, in other words. But roughly meaning it's either one less than it or all the way up to S minus 1 more than it, more than S times the arm. So that in this case, what I would do is just sort of put a star anywhere that it does satisfy this condition. So if you unwind this condition for this example, I'm going to fill in the stars here. These ones satisfy this condition of the leg being related to the arm. But for instance, the white one, let me draw an X here. That X that I drew in the upper left, when we zoom in, does not satisfy the condition because the leg is 2 and the arm is 0. And 2 times 0 is 0, and you can't be more than 1 more than that because it's slope 2. So you just kind of calculate the leg and arm, and somehow when it gets too far off of being slope 2, you cross it out. And so the path div in this case is the number of stars. So 1, 2, 3, 4, 5, 6, 7, 8. So we have a path div of 8 in this case. And so, oh, and I think I was going to do this example down here. Yeah, so let me just be more explicit about for slope 2, what that means is if your arm is 0, your leg can be 0 or 1. If arm is 1, leg can be 1, 2, or 3. And arm being 2 means leg can be 3, 4, or 5. Okay, so in the example, let me fill this in again. Path div was 8. And so div is path div plus tdiv minus max tdiv. And so that's 8 plus 6 minus 12, which is 14 minus 12 is 2. Okay, so to
Maria?
calculate the div, oh, go ahead. Was there a question?
I mean, it's okay if you don't have time to answer this, but
Yeah.
do you have any like intuitive explanation of this path div and how to think about it and what it means?
I have thought about this path div so much, and I still can't answer that. I think it's just somehow, well, I think Sean might have some answers for you as well, because it's sort of geometric. Oh, wait, maybe Andy's going to say something. I just saw him turn on his video. If somebody
Sorry,
does have
I
a
didn't
good
mean to unmute
answer.
myself yet, but I guess I was going to ask another question, which is, so sometimes there's these like zeta maps or like sweep maps on these
Yes.
objects.
Yeah.
Is it possible that if I take some kind of sweep map, that it's some area-ish thing?
Yes, it's more like that. I mean, not even just some area is there's actually this whole aspect of this paper that I'm not talking about here in terms of ranks and the affine SN story and affine Springer fibers. You can, this K by K rectangle, you can basically put a rank of each box, and like it is sort of inversions in the ranked boxes somehow. And like with some, there's other definitions of path div for sure, and other like maps that turn it into something nice. And this is just going to be the most natural one for this proof. And it's a big pain. I don't know. So yeah, I'm sorry. It's these statistics just are complicated, and I'm just very impressed that anybody came up with this at all. So I don't think I really have the answer to that. So
I'll ask one more question. Maybe this is what Monica's kind of asking, but she's too, she does want to credit her own work, but I know she's done a lot of work on some of these statistics, and I think in the case where there's no labels, right? So is there some way to think about it in terms of, I'm blanking on the name of these objects, Monica, maybe you can tell me, but this work you've done with Misha and Eugene and people, yeah.
yes.
About
Sorry.
like counting div in terms of affine permutations, something like that.
Mhm.
Um, yeah, I'm not, this path div, I have no idea how it connects with that.
Yeah, I think this will be clearer in Sean's talk, actually, Sean's talks, because that the geometry paper actually was where we had to do a lot of the combinatorics that related to the affine permutations, and those kind of dim statistics do come up too, and I don't remember if there's a way of directly relating it to this path div off the top of my head, but it also comes up in this story. So maybe I'll just say yes, Monica's work is going to come up in a couple lectures, and maybe that'll make it clearer.
Thanks
Yeah.
for the sharing.
Yeah, you can also ask Eugene, and I wish he was here because he would know more than I do as well. Okay. So yeah, so the way we connect these, so finally we're going to actually connect these two combinatorial objects together. We can connect between the stacked parking functions and the rational rectangular parking functions by making a stack out of the rectangular ones, by removing the labels that are bigger than n, and then defining stack heights in terms of how many big labels there were. So let me do an example, starting from this example first. So I'm going to copy this. Oh, I had a square over there because I was going to fill it in, but I'll just copy it down here. Okay. So what we want to do is we have n equals 5 here we calculated. So we want to remove all things bigger than 5. These are called big labels. So if things are too big, we just cross them out. So I realize this is getting to be an increasingly messy diagram, so I'm going to clear it up a little bit. Remove some of the ins. Okay. Let me just cross out some of the big numbers like 7 and 6. Those are bigger than 5. And 4. No, not 4. Sorry, 8. I meant that one. And then we just kind of shrink everything. So 2, 5 in the first row, and then 1, and then 3, 4. And this will always make a stacked parking function where we define the stacks as follows. So the stack heights are if B1 is the number of big labels in the first column, so in this case 0, and B2 is the number in the second column, and B3 is the number in the third column, and B4 is the number in the fourth, this would be 0, 2, 0, 1 in this case. And we say it's admissible if all the BIs are less than the slope minus 1, or less than or equal to the slope minus 1, which means actually for slope 2, we weren't allowed to have 2 that we delete in the same column to make a stacked parking function. So actually our algorithm is only going to be valid if we switch. I'm going to switch the 6 and the 4 now. So some of them we can't do this operation to, but it won't matter. If this was 4 and this was 6, then that would be valid because I would actually only have 1 that I'm deleting in each column. And then my parking function over on the right would change. So I would actually have 4 here, and then a 3 on top. And so my final actual dict path here would hug these entries. And then the stack heights is the height h sub I of the stack in column I is going to be s minus b sub I. So it's the slope minus how many you deleted on each step. So now if we're 0, 1, 1, 1, you actually just put a stack of height 2 in the first one because the slope is 2. So we have stack height 2 in the first row, and then stack height 1, and then stack height 1, and stack height 1 in this case. Okay, so that's how we're going to link between the rectangular parking functions and the stacked ones. And whenever we have a map between combinatorial objects and statistics on these objects, we want to ask, does it preserve the statistics, right? So it will. It's going to preserve area and part of div, right? But first, before we actually state those facts, we're going to generalize this map to the word parking function case, because what does it mean to remove the big labels if you have repeats, right? Now what are you removing? So we have to just define that away, basically. So the way we define it is if D is a k by k dict path, and B is any sequence, which we just pretend is our sequence of big label numbers, where B sub I is sort of, bounded by the number of labels in column I, and the sum of the B sub i's total is big K minus N, right? Then we define WPF sub B of D and the sequence B to be the number of the set of column strict labelings of the top BI boxes in the ith column. So I'm going to do an example of what this is. If I label just the top so many boxes, in this case, so we have slope 3 here in this example. So now we're allowed at most 2 of these big labels in each column, and we just kind of write them from the top down. This is something in WPF B of D and then 2, 1, 1, because there's 2 in the first column, 1 in the next, and 1 in the next. Okay. Then we also define small labels, right? So you can also label the small boxes, which are just the boxes we haven't labeled. So maybe I'd label these something like this. This is a perfectly valid labeling in WPF small of D and then 2, 1, 2, which is the complement sort of the B values. So we're just sort of defining away big and small and just like picking what are the big boxes and what are the small boxes. So we also say B is admissible if each BI is less than or equal to n minus k, and S is admissible if its complement is. So here's our actual map between the word parking functions on the small labels and the stacked parking functions. You just delete the unlabeled boxes, and then you set the stack heights again to be hi is S minus BI. So exactly the same as this map we did above. So this map is really F up here. And it's just we generalized F to these, small labeled parking functions, and we're just deleting the empty boxes that we didn't label with anything big. So here's the facts that we proved. And by the way, I forgot to say that the 3 authors on our papers are Gillespie, Griffin, and Gorski. And so we're GGG. And so every time I put GGG, it's our result. So the triple G theorems about this map F is a well-defined bijection. And not only is it a bijection, as combinatorialists, we love that it preserves statistics. So the area of a parking function pi, one of these small parking function pi's, that the area only depends on the dict path, and it's always equal to the area of the f of pi, which is also just sort of, the way you make the dict path is pretty clear. You delete the big labels and you hug the small labels. And then what the dinv does is hdinv, that expanded dinv that we defined of the stacked parking function, is equal to just the tdinvs on the small letters. Like if you only look at inversions among those small letters and you don't even count the big letters, then you take that tdinv of pi, and that's what's preserved. So this map is going to be really essential in connecting these two sides of the combinatorial equation with the skewing formula. And basically applying the skewing is what's going to separate things into big and small letters. So that's really kind of what's happening, is the skewing is cutting us down to size, and then we can just use this map to glue things together. Okay, so the next step of the proof is some algebra. So I kind of lied. I said this is a combinatorial proof, but we're also going to do some algebra in this one to set it up. Just basically to simplify the generating functions first before we actually do the full combinatorial bijections. So we need to use some LLT polynomials that we define both for these big and small admissible sequences. And actually these are defined even if B and S are not admissible, which is important. So FDB is the sum over all these big labeled word parking functions where you only label the big squares of q to the tdinv among the big squares, x to the pi big. And same thing for small, you sum over the small word parking functions, q to the tdinv small and x to the pi small. So I'm just labeling big and small and defining it away, and we're only doing the tdinv, not the dinv or the area or the path dinv or any of those complicated things. We're just doing the LLT based on the tdinv. So so we know these are symmetric because these are examples of LLT polynomials, and that's a whole theory in itself. Then we also define a statistic DSB that are going to sort of connect the big and small. So if you have an S and a B, we're just defining that to be the number of attacking pairs between the big and small labels, where we pretend every big box is bigger than every small box. So that means for like a standard parking function, for instance, tdiv is tdiv small plus the d of SB plus the tdiv big, because all the bigs are going to be bigger than all the smalls in a parking function that doesn't have repeats. Finally, we define a very important coefficient, CDB, to be max tdiv of D minus path div of D minus this DSB. And the reason this is important is because it's what we need to state our key theorem. This is like the keystone theorem that's going to like put everything together, and we're going to prove it next time. So I just need to state it so you can see why it's important. And then I'm going to go into why this is true next time. But the key inner product we need to compute is one of these FDB LLTs inner producted with our rectangle Schur function. It's the thing we're trying to skew by. And that's actually just a single power of q, this q to this CDB that I just defined, if b is admissible, and otherwise it's 0. So this FDB is defined for any tuple b, even if it's not admissible, even if it's not the right size to be big. And it kills it off if it's not the right size or if it's not admissible, and otherwise it's q to this single power. So this involves like a lot of combinatorics. This is where the teaser will come up, the sign reversing involution, all that. But we'll prove this next time. And today I wanted to just show how this, once we have this key theorem, we can finish up the proof in a combinatorial way. Okay. So, so the main theorem that we're trying to show is that this skewing formula, right, that we want to skew the rational shuffle, which again is this big K by little k rectangle stuff. When we skew that by a Schur adjoint operator, then we get the delta side, which is these stacked parking functions, right? And we want to show it holds combinatorially, meaning we want to sort of start with the combinatorial formulas in terms of area and tdiv and stacks and parking functions, and try to explain what this rectangle adjoint operator does to the left-hand side and why we get the right-hand side. So we're going to use these LLTs that we have here. So I think I'm just going to sort of trace over this because I wrote it out because I didn't want to make any mistakes, but I want to also go to a pace that everybody can follow. So I'm going to write it. So FD is because if I just point, you know, it's not as much fun. So the sum over W being a word parking function, and that's K by K of a dict path D of Q to the tdiv of pi, x to the pi. Okay. So this is yet another LT actually. And this is the one that when we can sort of relate to the FDS and FDB. And this is a very fun use of plothistic substitution to be able to get a handle on this skewing. If we plothistically substitute x plus y into this symmetric function, and I intuitively what that means is actually just doubling your set of variables where we have a bunch of x's and a bunch of y's, you know, x1, x2, x3, dot, 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 and y1, y2, y3, dot, 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 and you sort of plug them in for the power sum symmetric function basis or whatever. But in this case, you really are just sort of, you know, thinking of the y variables as sort of bigger than the x variables, but you're plugging them all in. And what you can show is it's the sum over all ways of decomposing into B and like big and small labels, where there's no restriction on admissibility or any of that, of Q to the number of inversions between S and B, but which counts towards this tdiv, right? If we sort of put it all together, you're going to have the tdiv between the big labels that are corresponding to the y variables and the small labels that are corresponding to the x, say, of then you'll have your FDS in the x variables times your FDB in the y variables. So I know plothistic substitution is sometimes confusing, so maybe I'll pause to see if there's a question, although I can't promise I'm going to define everything in full detail. Oh, there we Okay, so what's the advantage of this plethism operator is there's another formula for perping, actually, that I didn't really talk about before, but it's basically another application of the Littlewood-Richardson rule. Another way of taking an S-perp operator applied to a function. Plethistic. Am I saying plethistic wrong or something?
Oh, no, it's just I've not
Right
heard the
words.
word
Oh,
before.
what substitution? Oh, I see. Sorry, I didn't. Plethistic.
Having never heard the word before, I can't parse it when you speak it at any speed.
Yeah, okay. What I should write is it's like x1, x2, dot, 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 y1, y2, dot, dot, dot. So I have like an infinite set of variables usually that my symmetric function is in, and I'm doubling that infinite set of variables
Yeah.
into.
Well, you spelled that out before. The concept is straightforward. I was just curious
Got it.
what the word was.
Yeah, plethistic. So there's a lot more complicated plethistic substitutions out there than x plus y. But this one's fortunately not too bad to understand. So yeah, so then S rectangle of y, and yeah, sorry I didn't see the chat. I was just not looking. FD of x plus y. This is just sort of another formula that matches all the skewing and all this stuff. You can always take the inner product of a Schur function with the plethistic substitution in the two variables to get out what the adjoint operator is applied to the FD in the x variables, right? And so what that turns out to be is so if we can calculate out this inner product now by just using this formula that we have above for FD of x plus y, where we break it into the FDS of x and the FDB of y. So we have the Q to the SDB out front, right? Or DSB, sorry, out front. And then you have your FDS of x and your inner product of S rectangle with y with FDB of y, right? Because the inner product of the sy will only affect the y parts, and the x's are basically like constants that you take out. And so then the key here, the key theorem rather, says that this inner product, we already know what this inner product is. It's usually 0, but unless it's admissible, in which it's this 1 power of q. And so we go back down here, and now instead of summing over all b and s, we're only summing over the admissible b and s because everything else dies, of q to the dsb plus this extra constant that comes out of the inner product here, right? That's that extra constant power of q. And then you still have this FDS of x, right? So we're now back all in the x variables. We got rid of all the y's. Everybody's back to x. Finally, this CDB was defined as max tdiv minus pathdiv minus DSB, and so you plug that in, and we just get max tdiv of D minus pathdiv of D, which now only depends on D in the the exponent of Q, and then we still have to sum over the S admissible of FDS in this way. So now to apply this perp operator to the whole formula, we're gonna now sort of zoom out and apply to the rational shuffle. So this is really S. I should be writing S lambda perp of EKK of 1, which is rational shuffle, is S rectangle perp of this formula. This div, now let's remind ourselves, is path div plus max tdiv minus tdiv, and we plug that in. And what we're doing is we also can write it in terms of this FD LLT, which absorbs the which part? The tdiv part. Oh, sorry. I wrote this wrong in my notes. I was wondering why I got a negative sign. It's path div plus tdiv minus max tdiv. There we go. And the FD absorbs the tdiv from this, and so we just have path div minus max tdiv left in our Q power. So we're basically taking our polynomial, writing it, like grouping it into LLTs with these FDs. And then we apply this S perp, and this S perp goes inside and applies to this FD here, right? And at that stage, then we can use our formula for what we found above, that S perp FD is equal to this sum over bns admissible of q to the max t div minus path div of f ds. So what do we notice about this exponent, max t div minus path div, versus this exponent? Monica's going, they're canceling each other, right? So they cancel each other. That one comes in and the q's cancel. And all we have is this sum over db being an admissible pair of t to the area of d times this small LLT FDS. And now we know what this FDS is. It's the sum over d and b being admissible of the sum over pi in word parking functions of ds, t to the area, q to the t div small, right? Because we're just expanding what that FDS is, and then we defined it to be the sum over word parking functions that just use the small boxes with this t div small. And now finally we use this f bijection, right? Which we're scrolling all the way up. It's one of our facts. I'm going to go back to the facts box. So h div of f of pi is t div small of pi. And so now we just replace that t div small with h div basically and apply the f bijection. And what that means is that we're now just summing over the WLD stack polynomials f of pi, right, of area of f of pi, because area also is preserved under the map f, and t div small turns into h div, and we have x to the f of pi, and we just replace f of pi, right, with, you know, p or something, a parking function. Now this is a stacked parking function of t to the area of p because it's a bijection, q to the h div of p, x to the p, and that is the delta side. Okay, so I put my QED too soon, so. Okay, so that's the outline I wanted to do for today, and actually I have more time than I thought. So I sort of was rushed last time, and so I made sure to prepare it less and be, you know, more slow this time, but now I have lots of time for questions. So does anybody have questions on what I did here?
I'm tempted to ask, how did you discover all this?
That is a really good question. Yeah, and that's not something I was, you know, sort of okay, actually that is a good question that I can just sort of ramble about. The way I discovered the way he started discovering all this is actually from previous work of me and Sean. So yeah, so how, for instance, how did we notice the skewing formula? That's what I can answer. And the prior work is just GG, so that's me and Sean Griffin, actually noticed a skewing formula for the delta polynomials at t equals 0. And so maybe I should say, I actually mean, you know, the full delta ek minus 1 en evaluated at t equals 0. And that t equals 0 evaluation is related to, you know, so we have sort of a Schur expansion of this as well now. In terms of what are called battery-powered tableau. Okay, that's also a very fun thing we discovered. So there wasn't a Schur expansion known for this before me and Sean started working on it, and our entire goal was to actually find the Schur expansion for the t equals 0 delta polynomials. And what we did was we actually just wrote out a bunch of Schur expansions, found a bunch of patterns, and then found that it was basically the skewing of some other polynomials that came from it was a skewing operator applied to something else because we generalized a formula for the Hull-Littlewood polynomials. A skewing formula for the Hull-Littlewood polynomials that there's so many players in this story, I don't know where to start. These are the graded Frobenius of, and we'll talk more about graded Frobeniuses, but of the Garcia-Protesi modules. But the skewing formula actually used an en perp, right? And an e perp is basically, en is a vertical Schur function, right? It's S of a vertical shape is what I should say. And so there was already a skewing formula out there in the literature that took some, nice operator theoretic symmetric function and applied this skewing operator to it and got the Hull-Littlewood polynomials out. And we were looking at not just the t equals 0 delta, but a common generalization that came from Sean Griffin's thesis called the delta Springer polynomials. So there's also this delta Springer story at t equals 0, and that's really also what we're generalizing to q and t. There's these delta Springers that, so there's sort of how do I want to say this? There's the one variable co-invariant ring Rn, which is going to be, you have n variables x1 through xn, and you take the polynomial ring in n variables mod e1 through en, and you can generalize this in two ways. R mu is these Garcia-Protesi modules, which correspond to these Hull-Littlewood polynomials, which are specialized Macdonald polynomials. And then you can also generalize this to these RNK modules, which correspond to the t equals 0 delta conjecture. And basically, the Frobenius characteristic is what you get when you plug in t equals 0 for a delta polynomial. And what Sean did in his thesis was find a common generalization of these called R n lambda s, which is unfortunate. For this talk, I will just say, let's call it n mu k, right? So the point is now we have three parameters, n, k, and a partition mu. And there's also a sort of geometric understandings of this entire square in terms of flag varieties and Springer fibers. And so there's a geometric formula going on as well. And what we found was two things simultaneously. There was this geometric skewing coming from this notion of sort of I don't know. There's too many words. There's a geometric skewing that sort of generates these affine Springer fibers that Sean will talk more about. I'll just say that. And then we've also found a combinatorial skewing formula that allowed us to find a Schur positive expansion for the delta Springer polynomials. And so as a corollary, it gave us a Schur expansion for this one, and it specialized to the Schur expansion for this one. And what we really did was just take the known Schur expansion over here, and we guessed what the Schur expansion up above was, and we were correct, and we found that it matched the skewing formula, and then we proved all these formulas in one variable. So just t equals 0, we only had q, we only had x's, we didn't have y's, all that. And so then when we started thinking, does this generalize to the full delta conjecture in any way? We talked to Eugene Gorski, who knew a lot more about the rational shuffle stuff and the rectangular parking functions, and that was how we put it all together and generalized it to two sets of variables. So I'm really glad you asked that question, because this is like a whole part of the story and motivation that I just didn't have time to prepare. And I hope this was sort of vaguely understandable, because there's a lot of moving parts.
No, it is quite understandable. You have a bunch of objects that have been created in the past, which have various their generalization relationships. And then you say, well, can you combine these generalizations? Then it touches on something else, and you say, well, can you generalize in that way? So there's a sequence of generalizations you went through. Yeah. And presumably at each point, the combinatorics, the proof getting messier and messier.
Yes.
But that way you don't have to create the thing from the whole cloth in one step.
Yeah. Oh, and actually, I want to say one more thing that I planned to say today and I just forgot, which is when I did the overview last time, let me go back to the overview slide. This one. I said this thing down here, and I think I wasn't entirely accurate. It's true that you can think of this as this combinatorial proof as combining with the algebraic skewing formula to give a way of deriving the rise delta formula from knowing the rational shuffle statistics, because those statistics will just sort of come out of the bijections that we'll make. But first of all, you can't go the other way because we're skewing. It's hard to unskew. It's easier to skew than to de-skew yourself. So coming from delta to rational shuffle will be harder. But also, one corollary of all our picture here, and I'll write that at the bottom, is that in terms of finding sure expansions for these, I mean, that was our goal in one variable. And we sort of at least have a implication here. Any sure expansion, if we can figure out the sure expansion for the rational shuffle, this will automatically give us a sure expansion for delta, right? And the reason is just that, so the proof is that, S perp of something sure is just skew all the sures, right? And apply the little bit of Richardson rule, right? So we know how to do that, which means we've reduced it's at most as difficult to find the sure expansion for delta as it is to find the sure expansion for rational shuffle. So it's one of these things like, if we can prove the Riemann hypothesis, then we can also prove this, So I don't know how hard any of these are, but it's an implication, which is kind of fun. Okay, and then Martha asked, is there a geometric interpretation of the skewing operator? And yes, and I'm just going to completely leave that to Sean because he's going to be doing a better job than I am on that. So come back in 2 or 3 lectures and you'll find out.
All right, thanks, Maria. Such a great job. Thank you.
Thank you.
Any further question for Maria? All right, if not, then I will see you everybody on next week, Tuesday, same time. Maria will continue with the combinatorial proof.
Yes, thank you.
Thank you so much. Have a nice weekend, everybody.
Bye, everybody.
Bye.